What is the connection between polynomials and Fermat's last theorem? Imagine trying to solve a puzzle where the pieces are polynomials instead of numbers. That's where the connection between polynomials and Fermat's last theorem begins. Fermat's last theorem states that for any whole number 3 or greater, the equation to the power of n plus y to the power of n equals z to the power of n has no solutions where x, y, and z are non-zero whole numbers. Now, what if we replace those numbers with polynomials? That's the question mathematicians ask next. A polynomial is an algebraic expression made from variables and coefficients, combined using addition, subtraction, multiplication, and non-negative whole number exponents. For example, x squared plus 3 times x minus 5 is a polynomial. Factoring polynomials means breaking them down into simpler polynomials that multiply together to give the original. Polynomial operations include adding, subtracting, multiplying, and dividing polynomials, as well as raising them to powers. In the polynomial version of Fermat's last theorem, the question becomes, can there be non-constant polynomials f of x, g of x, and h of such that f of x raised to the power of n plus g of x raised to the power of n equals h of x raised to the power of n? This is similar to the original equation, but instead of numbers, we use polynomials. The answer is that for powers 3 or higher, there are no such polynomial solutions if the polynomials share no common factors. This means that just like with whole numbers, you cannot find non-constant polynomials that satisfy the equation 4 powers 3 or more unless they are trivial solutions, like constant polynomials. The proof of this fact uses basic algebra, especially polynomial operations and factoring. It also involves understanding the properties of polynomials over fields, which are sets where you can add, subtract, multiply, and divide polynomials without issues. Studying these polynomial analogs helps learners see how algebraic structures work in broader contexts. It connects a famous number theory problem to the world of polynomial algebra. Concepts like cuprability, which means the polynomials do not share any common factors, and polynomial degree, which tells us the highest power of the variable in a polynomial, are key ideas here. So, in summary, polynomials are algebraic expressions built from variables and coefficients. Fermat's last theorem says no solutions exist for the equation to the power of n plus y to the power of n equals z to the power of n when n is 3 or more, 4 whole numbers. The polynomial version asks the same question but with polynomials instead of numbers. It states that no non-constant polynomial solutions exist for powers 3 or higher if the polynomials are coprime. This connection shows how the ideas of polynomial operations and factoring relate directly to a famous problem in number theory, helping learners see the power of algebra in understanding complex mathematical ideas.